thing is, if you don't know what the procedures are, then you're kind of in a jam, right? So I found this cartoon online. I'm not sure if I was legally allowed to take it, but I did anyway. But it's got a citation of who it's produced by, so I think it's good. There's some guy named Mark Anderson. Did a wonderful job. I wish we hadn't learned probability, because I don't think our odds are good. Yeah, sometimes ignorance is bliss. You just don't know the nature of a situation. You can kind of work your way through it and walk in a tightrope. Gravity is not a concept that crosses your mind even a little bit, and a tightrope is not even remotely dangerous in your mind. Probability, branch of math deals with the chance of an event occurring. An event is a collection of outcomes of a procedure. A sample space is a sample space with a complete list of all possible outcomes in an experiment or an activity. Okay, so we're going to spend basically the whole unit working with those ideas, events and sample spaces. Folks in the past have had a little bit of difficulty distinguishing between events and sample spaces. The key for the sample space is that it's all possible outcomes in an experiment or an activity. So I'll just throw in a small example here, very minor. You have a red marble and a black marble. In a bag. So it's just two marbles, that's it. All right, so very straightforward. In terms of probabilities, this is a question that you wouldn't need me to teach you how to figure out the answer to. If I were to say, find the probability of getting a red marble. Might as well write it in red. I had a choice, so why not? All right, so we won't actually find the probability. I just want to use this example to talk about the event and the sample space. This is the event. All right, I might have had more than one red marble in there, in which case my question might have been, find the probability of getting any of the red marbles. All right. Or I might have taken a marble out twice, in which case I would look for maybe the probability of getting two red marbles, a red marble and a black marble, both black marbles if you have more than one, that kind of thing. But whatever it is that you're looking to find the probability of, that is your event. All right. Now, usually the framework of the problem tells you what the sample space is. So this given information is what we have available. That's a sample space. Okay, because that's our set of possibilities. All possibilities. If I were talking about flipping a coin, my sample space would be heads and tails, because those are my possibilities. But if I get specific and I said, what is the probability of getting heads when you flip that coin? Now I know the event. The event is getting heads. Right, so just that terminology is worth spending a little bit of time on, because it is a little bit of a weird adjustment if you have no experience, no prior experience with probability. Notation, P for probability. That'll be kind of aggravating down the line when we use P to represent proportion and like 5 other things. But their definition, those 5 other things, their definitions are always rooted in probability. Right, so it's something like we'll deal with a p-value in the 3rd unit. That p-value is, you guessed it, a probability value. It's just a question of probability of what, So we distinguish among the context, but the p always represents probability, right? And when I say it could represent proportion, a proportion is a fraction. A fraction could be converted to a decimal, and if you have the right kind of decimal, that decimal could also be thought of as a probability. So it'll come back in that way also. All right. We stick to the beginning of the alphabet for specific events. I only wrote A, B, and C. I don't want you to think it's limited to A, B, and C. In fact, I'll take that as a typo. Um, I wrote this, I think, 18 years ago, and I never changed it because I thought it was good enough. But right now, I'm seeing it could be a little bit better. Maybe a dot 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 after the ABC to indicate that we can use D, E, F. Eventually, you'd want to stop. You don't want to go too far past the middle of the alphabet because then those letters are usually reserved for other things. So, once you get to M, I would say quit it at that point because N is gonna start specific things. In fact, we already know what N represents. It represents the number of values in the set. O, well, we tend to stay away from O as a variable for the most part because O looks an awful lot like 0. And that gets confusing when you try to put together an algebraic expression. P, we know P represents probabilities. Q is also going to be a probability term. So, long story short, those are already kind of reserved. Now, if you're dealing with a problem where you have more than 10 events, odds are you didn't get that from me, right? Because it's not going to be like, all right, here's a deck of cards. Find the probability of getting a jack of hearts or a queen of diamonds or a 10 or a 2 or a black card, or like it just doesn't serve any purpose to ask it in that kind of way. Right? You can get the idea across by saying, find the probability of getting a red card or a jack or a king. Three events is usually good enough to get an idea across. So there are a few different ways to determine probability. We have the experimentation approach, we have the formulaic approach, and we have estimation and pattern recognition. The experimentation approach is what you do when you have really no information whatsoever. It's also known as an empirical approach, but I don't think that's really necessary to get into. Because we had an empirical rule in the last unit. And, I don't imagine too many of you will be taking the final exam, but for those of you who are, it's a cumulative exam. So if I have the empirical rule and I call this the empirical approach, you might get confused, and I don't want to do that. All right, so we just call it what it is, experimentation. I have no idea about the nature of the situation, so I'm just going to experiment to figure it out. And there are rules to experimentation, and I'm not even talking about like the humanity type of rules that might be out there, like don't experiment on humans with like lethal, potentially lethal things. They used to, but it's just horrible when you think about it. Like I don't even want to go too far down that road. It's just terrible. But yeah, like if I did not know, and I used a simplistic example here, but if I did not know what the probability was of getting heads when I flipped a coin, I could flip a coin a bazillion times, or 10 times, or 100 times, whatever, some predetermined number of times, and see what the outcome is. Yeah, you would think roughly half the time it would be heads, and the other half of the time it would be tails. But I don't think you'd call BS on it if, let's say, you did 100 trials and you got 51 heads and 49 tails. You're gonna be like, those mathematicians are full of crap. 0.5 my ass. No, it's you're gonna be like, well, that's pretty close to what it ought to be. There's some variation, weight of the coin. Maybe I'm not a good flipper. A lot of different things going on there. Or maybe it's just shaken out in the long run. Maybe I need to flip it 500 times or 1,000 times or 10,000 times. So instead of flipping a coin 1,000 times yourself, you just get 9 other people. You flip it 100 times and have those 9 other people flip it 100 times, and then you share your results. You compile it all together. And that's a good way to go about doing it because, one, you're not worried about your own perception, losing count. The more you try to, like, if I were handed a stack of like 30 papers to proofread, I'm not going to do as good of a job as I would if I were given a stack of 2 papers to proofread. I could spend more time, I could be more careful, I'm not going to get tired and bored, right? So you split the work that way. Also, it allows for you to vary the different ways in which a person might flip a coin. So you're not dealing with what we call a lurking variable, where maybe you just didn't do it in a sufficient way to get the desired outcomes. We're varying it up a little bit. So That is, I mean, we're calling it experimentation, but the foundation of that concept is something called an experiment. And in the third unit, we get into all the different ways in which a person properly conducts an experiment. And what I just described is kind of a precursor to that. All right. But yeah, you could do it. Yeah. 200 times. You'll get a sense. Sometimes that's all you need. Sometimes you don't need the actual answer. Sometimes you just need an idea of what the answer is. I think of a game of chance like roulette. Like, I don't know precisely that day how many times the number 8 came up on a particular wheel, but I know if it hasn't come up in a while, it's probably going to come up at some point, more likely than it would have otherwise, because 1 out of 38 times the number 8 should come up on average. But maybe I only observed like 100 spins and I didn't see the 38. That doesn't mean I'm about to get 2, 3 consecutive. The 8. That doesn't mean I'm about to get 2 or 3 consecutive 8s. It just means that the probability of getting an 8 has been nudged a little bit more in my favor. And that I didn't do any math for that. I just have a sense based on witnessing the situation and using what I know about probability. All right, so sometimes, again, we don't need a number. We just need an idea of what's happening, what the probabilities feel like. All right, so, but a law of large numbers, as the number of trials in an experiment increase, the observed probability gets closer and closer to the actual probability. Law of large numbers and something called the law of averages, you may have heard that. The law of averages is really kind of weird because it's a very commonly misused term in real life, and we don't really do much with it in this course. Law of large numbers is stating what I'm talking about. As you increase the number of trials, you're going to get closer and closer to the true probability. All right, but usually when they talk about law of averages, in a sporting context, there was a classic example from a textbook that said Michael Jordan took 10 free throws and made 5 of them. All right. Next time he's up, what would be the probability of him making a free throw? It depends on what you think about it. If they gave some background information, like his career average is at 90% or something like that, then you would say he's got a 90% chance of making the free throw. But you wouldn't look at it and say, well, he just only made 5 out of 10, so he's more due to make a free throw. So it's almost guaranteed now. Like he's not going to miss like 5 straight and then miss another one after that. So he's going to make the next one, 100% chance, because they figure that those free throws themselves, the percent of successes on the attempts that he makes, like in a game or over a course of a season, would have to eventually come out to be his career average. But that's not how it works. That career average just gives you a sense of what he's capable of. But it's still an independent event every single time he takes a shot. You could even look at it as 50-50, but that's probably not true because you're talking about a professional athlete, like world class, like best ever. I don't care what they say about the new guys. So, you know what? The whole LeBron James, Steph Curry, Kevin Durant, anybody in the prior, I'll call them generations, Kobe Bryant, all those guys, they're all really, really good. None of them transcended the sport like Michael Jordan. He's one of those people where, like, I don't stay up late. I didn't stay up late to watch a Lakers game because Kobe was playing. I won't stay up late to watch a Warriors game because Steph is playing. But I would go out of my way to watch a Bulls game because Jordan was playing. And because I'm a Knicks fan, that's saying a lot. Because there was that intense rivalry where, like, we loved him so much we hated him. That's what it was. Because it's like, oh my God, how did they get this guy? And he's going to beat us again. We were up like 2 games in a best of 7 series, or best of 5, I think it was at that time. And they're like, yeah, we have no chance of winning this. Like, we already have 2 games in the hand, All we have to do is win one more. I was like, I don't see how we're winning another game against this team. Like, and we just won 2. So, Yeah, it's Michael Jordan. So any kind of basketball references should, if you're dealing with, ideas for a project or something, which we'll talk about more as we get towards the end of this unit because it starts to become more and more relevant. But, like basketball projects, comparing different eras, different individuals, salaries over different eras, those are all pretty interesting. But it'd be even more interesting if it was like this guy versus Michael Jordan, that guy versus Michael Jordan, that lady, go WNBA. Best ever for the WNBA against best ever from the NBA. Make a case that the WNBA player is better. I don't know. You could do a lot of things. But this is going to kind of inform your thoughts on that. And again, not just basketball, soccer, anything you can think of. The opportunities are pretty much endless. The formulaic approach in class, that's pretty much where we're living, right? I'll give you some formulas. We'll learn when those formulas apply, and then we'll use them. All right. Sometimes, and this is where it gets tricky, and this is the case for any probability course, introductory or even more advanced. There's a part of the course where everything seems like, oh, this is not bad. This is great. It's easy even. All right, cool. I think I'm going to get 100 on this one. And then all of a sudden it's like, bam, brick wall. What the hell is that? How'd you get that from that? So just, I'll try to point out that moment, but I'm going to go out on a limb here and say, I don't think I'm going to need to point it out. You'll know it when you see it. Because it goes with like, let's take a marble out of a bag to quality control inspection. And it's like, wait, how does probability fit in there? But you'll see, it's pretty cool. Right? But the big challenge here, in almost all cases, is making a determination of what formula to use under what circumstances. Right? So I'll gear you towards that, give you some keywords and stuff. But if you can internalize it and make it your own, you'll be better for it. The third type is estimation pattern recognition, least frequently used. I've been meaning to change this one for years. I say mathematically. That's not really true. Just in this class. So I'll make that adjustment if somebody wants to submit that for a typo, because it's very frequently used mathematically. We estimate and determine patterns all the time. So I don't know why I wrote that, but I did. So anyway, yeah, pattern recognition. That's the movement of data over time, over space, whatever. And it's really kind of cool because if you can kind of, and it's a little trickier because if you don't have a calculus background, it may not be as easy to see the relationships, but in a lot of cases you can. If you have data points that for a low number of trials are kind of like really deviant from whatever the probability is, let's say this probability is 0.2. It really deviates. But then later on down the line, as you increase the number of trials, it gets closer and closer to that number. And again, this is for large N. For a large number of trials, you're getting closer and closer to a particular value, in this case 0.2. What you're actually finding is a limit from calculus. It's the limit as the number of trials increase. And what that limit would represent is the actual probability, because what we would be learning is as you increase the number of trials, what the percentages are approaching, what they're getting closer and closer to. So sometimes those percentages converge on a particular number, in which case you can get an answer through pattern recognition and estimation. Sometimes they diverge, meaning that they never actually close in on a particular value. So maybe it's the opposite of this, where for a small number of values, it's really close to a particular number, but then as you increase the number of trials, it gets more and more spread out. That's inconclusive. There will be a probability associated with it. It's just not something you would determine with this kind of technique. All right, so a good example, weather prediction based on past experience. All right, so, if you start collecting data now, October 13th, 2018, you look outside, and that's all you have to do, look outside. See some rain. You could even go outside, collect the temperature, write that information down. You could, if you have a barometer, get the pressure, make note of it, then next year do the same thing. You might have two wildly deviant results for those particular days. Maybe we have a late summer next year, and it's like 78 degrees on October 13th, and it's a bright, beautiful sky. Right? So now you're as opposite as you can get. Then the third year, maybe we have a freak snowstorm. All right? So we're really all over the place. But if you keep doing that year after year after year, 100 years later, more often than not, you're going to have a true representation of what the weather would be like on this particular day. Because after that 100 years, maybe you only have the one or even two freak snowstorms. Maybe you have like 10 or 12 instances where you have a bright sunny day with high temperatures, but the rest of the time it's going to be cold and crappy out. So you have a sense through pattern recognition of what you're converging on in terms of the conditions. Right? So it's pretty cool in that regard. Although you don't want to have to wait 100 years. Fortunately, somebody's been doing this for a while, ever since agriculture began. They've kind of really had to have a sense of what the temperature was going to be and the conditions outside, because it's like, okay, when's harvest? When am I planting? When am I, like, when's all this stuff happening? Am I going to plant everything to find out that I'm about to hit like the hottest, driest part of the year and everything's going to die? No, I want to know that information before I start planting my crops. Right? So very, very important stuff and very meaningful. Basic probability rules, always between 0 and 1. Therefore, probabilities can be represented as fractions, decimals, or percents. I recommend fractions not because I'm a math teacher, and math teachers, for some reason really like fractions, but because you'll have an easier time providing an exact answer in fraction form. You generally don't have to round fractions. So you don't have to worry about rounding instructions, rounding rules, losing credit for that kind of stuff. And also, it's exact. What could be better? So yeah, and I've experienced this over the years, and it's, I hate to say it, there are certain indicator questions or things that students do on tests and quizzes that show me you really got a good sense of what's going on. Even having a good sense of what's going on doesn't always lead to like a 100 on a test. We make careless errors all the time, all of us, myself included. But then there are people who make the kind of errors that I'm like, were you in class at all? And if so, were you awake at all? And and even in those cases, I'll look at it and be like, okay, so given the fact that you were absent or asleep whilst in class, you still should have known that your probability for, I don't know, winning a bicycle in a raffle, you should have known that that's not equal to negative 0.7. Like, it's just, I just think it's, how would a negative fit into this concept? I don't see it. If we think, I'm saying 0 and 1, 0 means impossible, 1 means must happen. This is the same as saying 0% of the time, and this is saying 100% of the time. That's if we want our answer in percent form, which we generally don't, unless you're asked specifically. But to get an idea, that's what our interval is, 0 to 100%. So you could have growth, like a human can grow by more than 100% over a period of time. It just means that they'd have to, I don't know, more than double their height or weight, which, I mean, that's a rapid rate of growth, but I suppose it could happen. I mean, if you allow for a long interval, it definitely happens, because over your lifespan, at some point, you were half the size that you are now, and probably half of that and half of that. Otherwise, someone was really, really uncomfortable in the beginning. So, like, these are our, I mean, it makes sense in that context, but these are our rules for probability, because if I'm saying that I'm going to roll a die, six-sided number cube, for those that don't know what a die is. Die is the singular of dice. I'm going to roll a die, and let's say I'm going to ask for the number 1. All right, that's not going to happen more than 100% of the time. It's going to happen at some point, 1/6 of the time, but it's not. You can't get that to happen more than more than what? The number of times you're even trying it? That would be like saying, I flip a coin 5 times and got 7 heads. Yeah, that's the best I can come up with in terms of why more than 100% wouldn't make sense. How can you have more than what's available unless you're creating them on the fly? All right, so 0 is impossible, 1 must happen. It's a certain event, but it's not saying that it always happens. It's saying that it must always happen. That's 2 different things, because I can say that I flip a coin 5 times and get 5 heads. That's not a probability of 1. I mean, conceptually in this context. It's really, we still would leave that as 5 over 5. Because 1 is telling us that it must always happen. So I would say that that probability is just 5 over 5, that experimental probability. Its theoretical probability of getting a heads, is still 1 out of 2. Unless it's one of those trick coins. All right? So 5 out of 5 is not always going to be equal to 1. Now, if it was a trick coin where both sides were heads, and I said find the probability of getting heads, well, you must always get a heads, right, if you flip a coin? So that would be the case of 1. We don't assume any significant width on the side of coins when, for academic purposes, quizzes, tests, things like that. Just to stave off the inevitable question, what if the coin lands on its edge? And I'm like, Saturday morning, dude. Can you just stop? It's either going to land on one flat side or the other flat side. We're going to assume that we're not violating any laws of physics. All right, complement rule. So the notation strikes again. P of A plus P of tilde A equals 1. Okay, well, let's go back and take a look at what that means. P of A means the probability of event A occurring. P of that symbol means not. Simply it means not. But we could also think of it as the opposite. And in fact, I would say the term opposite actually makes more sense for what we need it for, but it's just easier to say P of not A rather than P of opposite of A, P of complement of A. All right, so in my side example here, I asked for the probability of getting a red marble. I could have said find the probability of getting a marble that's not red, in which case you would think that's where probability can get a little weird. In this case, it wouldn't be bad, but you would be thinking, all right, well, if it's not red, what is it? In this case, it's black, but in other situations, it might be, you might have other possibilities, and you have to account for all of them. All right, so there's little tricks of the trade that help us with that. All right, so the corollaries, the also, P of A is 1 minus P of not A, and P of not A is equal to 1 minus P of A. They all come from this rule. All right, 2 opposite events have to add to equal 1. So if I say the probability that it's raining is 30% or 0.3, and then the probability of it not raining is 0.7, that would be everything left over in the 0 to 1 interval. Those 2 numbers would add to equal 1. So along those same lines, we have this example. Given a multiple choice question with 5 choices, what's the probability of getting the correct answer by guessing? When we say guessing, that's including an element of randomness. Which means probabilities at work. Anytime you take randomness or randomization out of a situation, probability is less functional. There may be some what we call probabilistic, it's a fancier way of just saying probability-like aspects to a situation, but it wouldn't be fully probability-based. This one is completely at random, which means that this individual did not study at all for this quiz, or this question, is completely unprepared. It might be the case of some sort of pre-assessment. You walk into a course, the teacher wants to see what you know about, the course that you're about to take. So he gives you a couple of questions. not expecting most people to know how to do any of them. So what do? You're like, I don't know. That's why I'm here. I'm going to take this course to learn this stuff. But I don't know what any of this means. So choice C it is. That's the idea there. A complete random guess. And even that might not even be random, because if you're more inclined to select choice C, I know some students that are like, SATs, ACTs, AP exams, Regents exams, whatever. They answer what they can, and then they just put choice C for everything else. So it's not really random. It's just they have some sort of scheme behind why they selected that. It might seem random to us, but it would be really random if that individual spread out the guesses. Like in each case it was a different guess, and that's not done by natural perception. That's done usually with the use of some sort of randomization device. Sometimes a die. I mean, I think it'd be weird to take a die to a test and start rolling it. Although, from my perspective, that would be kind of funny, because I'd be like, all right, you're clearly guessing on that one, But yeah, I mean, your calculator has random number generator built into it, and we're going to learn how to use that. So these are ways that we can get random values so that we're not actually using our own perception. So anyway, probability of getting a correct answer. Well, there's 5 choices. So my sample space would be made up of 5 elements. Possibly A, B, C, D, and E. Maybe 1, 2, 3, 4, and 5. Something along those lines. We're assuming, because we have to, I think, that it's a traditional multiple choice question where there's only one answer. So you have a 1 in 5 chance of getting it right if you were to just take a shot in the dark and guess. The probability of getting it incorrect. Common sense tells us that if one of those 5 choices is right, then the other 4 have to be wrong. I didn't need any kind of rule to tell me that. If we know the nature of the situation, you say, okay, well, one's right, the rest have to be wrong. But let me write this differently. I'm going to write that as P of C. And this one would be P of not C. Because incorrect is the same as saying not correct. Turn the volume off on this. Now the rule up here tells us that if I take these 2 things and add them together, I'm going to equal 1. All right, so the complement rules has P of A and P of not A. It doesn't always have to be A. A represents some event. I just chose to denote my event with the letter C here instead of A. That's not a big deal. All right, so we have a 1 out of 5. We have a 4 out of 5, which is 5 out of 5, which is 1. All right, just the simple math gets us to a result of 1.